Good evening, everyone. I'm happy to welcome our speaker for the public lecture, who is Dr. Lisette de Pillis. Dr. de Pillis is the Norman F. Sprague Professor of Life Sciences and a Professor of Mathematics at Harvey Mudd College. She's passionate about using mathematics to seek solutions to real-world problems. She works with biologists, oncologists, biotechnology researchers, and other mathematicians to search for new ways to treat diseases that interact with the immune system, in particular cancer, HIV, SARS-CoV-2, and type 1 diabetes. Dr. de Pillis has been recognized for her multidisciplinary research excellence with the Maria Geppert-Mayer Distinguished Scholar Award from the Argonne National Laboratory. She was also a HERS, CBL, Claire Booth, Lucia Leadership and STEM Scholar, an Intercollegiate Biomathematics Alliance Distinguished Fellow, and a Fellow of the American Mathematical Society. Please join me in giving a warm welcome to Dr. de Pillis.
Thank you, Zach. I hope, can everybody hear me okay from back here? Great. And thank you, Professor Barton and Professor Bradshaw for inviting me and for all the folks who helped make this come together. So before I get started, I want us to get set up so that you can send me feedback during this talk. Okay. So to do that, we're going to use poll everywhere. Has anybody in here used that before? Okay, it's easy. Does everybody have a phone or a laptop with them? I mean, I will not, this is where I will tell you, take out your phone or laptop. I will not scold you for doing that. Okay. So, oh, interesting. We thought this would work, didn't we?
No.
Let's see if I can get it to advance. Okay. All right, so this is what it looks like. So you're going to use your phone or laptop, tablet to respond, and you can participate by sending either a text message or visiting the URL that I'm going to show you. They're both up here, but I'm going to go to the next slide and show you in particular. So, for example, you can send a text to, is it visible up there? I can't tell. Can you see it? It's to Lisette D971. Can you see that up there? It looks a little small. Okay, so you text, who's using their phone? Okay, so text 22333. And we send that to Lisette D971. So here. Apparently it was popular to use these things today, right? Does this work? Okay, so to 22333, right? D971. Okay, so actually put in text message. Text to that connects you to the poll. Okay, you can do that. In which case you can then just text, for example, if you want to send in the choice B, you just text the letter B, okay? But you can also just go to the website, okay, and answer by just clicking your selected answer. Okay, so again, the website is, goodness gracious me, oh my. It's POLLEV.com. Okay, so let me go back and make sure that this is here because it's much more fun if you can do this. Okay, so there you can see the text, Lisette D971, and here you can see the website to go to. Can you see that okay? All right. Okay, this one is a little bit easier. You don't have to register or anything. You don't have to give them any information. Just go to the website, put in that keyword, and you'll be on the poll. Okay? Okay. So, okay, let's give it a try. Let's see how this works. So this is to find out about you, because all I know is there's at least one undergraduate student in this audience, and I don't know anything else. So are you a student, a faculty member, staff, or you're just for fun? So now go to the poll in whatever way you want and answer the question and see what happens. I'm just going to ask you, raise your hand. I just want to see who you are. It's so fun to watch it, like the little bars slide around and see things happening. It's so great when it works. Okay, so who in here is a student, undergrad or grad? Okay, and faculty? Okay, so anybody, staff? Oh, staff. Anybody here just for fun? Okay, so we're half students, half faculty. Okay, that's good. I promised I would make this accessible, and we'll see how well we do. I'm gonna zoom along. Oh no, I'm gonna zoom along here a little bit. See, this is more fun with a poll. I love math. I somewhat agree. Let's agree to disagree. It's a love-hate relationship, and I'll decide after this talk. Okay, you don't have to answer that question, but that's also fun when it's a poll. Okay, and I'm gonna skip this one. And I'm just gonna, so this one actually has to do with working with others or on your own. So do you prefer, just think about it to yourself. Do you prefer to work on your own or with others? And this is my experience with others, as long as there are no slackers in the group. With others because I want to be the slacker in the group. Or I'm not sure what you mean by work. So just, think to yourself what that might mean. But I will say that in the work that I do, it's way more effective when I can do it cooperatively and collaboratively, because as many of you now know, I'm an applied mathematician. And so I do have to acquire domain expertise in the areas of application in which I'm working, but I also have to bring to bear the mathematics that are used to solve the problems we're interested in, which means that we need a lot of good brains working on these projects. What you see here are a bunch of some of my undergraduate students that have worked with me over the years. It's not all of them, but it's a sampling. And they've gone off to do a bunch of different things. Not everybody became a math professor, although a lot of them did. Some of them became physics professors. And actually, some of them went into industry, and at least one is a veterinarian, and one is a software engineer, and one works in genetics. And so my message there is that with mathematics, you can pretty much go and do anything you want. And so this was collaborative with new and future mathematicians and biologists. So here's the plan. I'm just going to talk about mathematical models and the way you probably were first introduced to them as little kids in school. Remember story problems? Did you love story problems? That's what they were called. Those are math model problems. We'll talk about a couple of famous math models, and then a basic cell growth model, disease modeling, SIR, which you've probably heard about now. Herd immunity was a term that was tossed about quite a bit back in 2020, 2021. And so we'll talk a bit about what that is. A predator-prey model is another very classical model. And let's just get started. If you get nothing else out of this, this is the message that by making a few simple assumptions, we can actually draw parallels between natural systems that may appear radically different on the surface and unlock new levels of understanding. And hopefully we'll be able to show you a bit of that. Okay, so if you want, you can raise your hand, but here are the choices. Your familiarity, your current familiarity with math modeling. You are an expert and do it all the time. I know some people here can answer that in the affirmative. It's pretty good. You've seen it before. It's minimal, but it exists. It is non-existent. Is it anything like runway modeling? And is it spelled with one or two L's? So ponder the one or two L's question, and I will come back to that. Okay, I'm not going to ask you this because clearly the poll doesn't work. So what is a model? It's a representation of reality, but it is not reality itself. That's important to keep in mind. So there are a lot of uses for a model: simulating outcomes or explaining why something happens, or creating a new hypothesis, or testing hypotheses, or predicting future behavior. There are all these things that you can do with a model. Now, the kinds of models that we have seen ever since we were kids were, for example, model trains. And I think you could say it is a representation of a real train, but not a train itself, right? Or a runway model, a representation of what someone might look like in that outfit, but probably not in real life, right? So all of those things are models. Now, when you work in this area, especially in math biology, you actually have to be careful with this term, because I learned pretty quickly early on that when I say model to a biologist, they're thinking mouse model and not math model. So you have to actually prepend what kind of model you're talking about. Okay. All right. So here is our story problem that we all love so much. Okay, we've been exposed to these problems since grade school. This problem was originally posed in 1942 in the book Differential Equations by Ralph Palmer Agnew. Okay, and the problem is this. One day it started snowing at a heavy and steady rate. A snowplow started out at noon, going 2 miles an hour and 1 mile for the second hour. So 2 miles in the first hour, 1 mile in the second hour. Okay, we understand the setup. What time did it start snowing? So is there enough information in here for me to answer that question? Well, it turns out that if I handle this carefully, there could be. Now, what Ralph said was our first task is to try to recover from the shock of being asked to solve such a problem. So that's in this 1942 differential equations book. But then he goes on to say that it is not a pure mathematical problem. Okay, it is one that provides all the hypotheses required for determination of an answer. It does not provide those. Rather, it's a real problem where we are forced to make physical assumptions. Okay, so making assumptions is key. Okay, and understanding and clarifying what those assumptions are is important. And be courageous, but be reasonable and try to draw correct conclusions. Okay, so here are the things that we think about. I see that the snowfall's steady. It started at noon. I went 2 miles in the first hour and 1 mile in the second hour. So I can use that to make some assumptions. The snowfall is constant. And I'll say that the snowplow speed is about 1 over the height of the snow. Okay, it's a big assumption, but it's a simplifying assumption that allows me to set up the model. And so I'm not going to go through the details, okay, but I'll just say you have to make some observations about when it started snowing and so forth. What are you going to call distance? What are you going to call height? Importantly, what is it that you're going to solve for? And what we're solving for is the hours before noon when it started snowing. And that will tell you what time of the day it started snowing. Okay, and it turns out this is not a very complicated problem. It is something that turns into a separable differential equation. So people who are mathy people, you'll know what that is. If you're not, don't worry about it. But what you find is a solution to a quadratic, which actually gives you the golden ratio in this particular case because of the parameters that we chose. And we can say it started snowing at 11:23 a.m. with our assumptions. Okay, so it can be pretty powerful. All right, so let's move on to models that people actually have used in the past in biology. So Leonardo Fibonacci, who is also called Leonardo Pisano because he was from Pisa. He was a medieval Italian mathematician, born around 1170 or something. He is actually known for creating one of the earliest mathematical biology models that we have become familiar with. So he posed the following problem. If you put a male and female rabbit into a field, how many pairs will there be after a year? Now, he's making simplifying assumptions, right? So he's assuming that it takes a month for a rabbit to mature. A mature pair produces a new rabbit every month. All rabbits remain in the field. No rabbits die. There are no predators. There's enough food and so forth. Okay, these are all simplifying assumptions. But then you can draw this picture that helps you figure out what this is going to look like with those assumptions. Now, it's not the most accurate way to count rabbit populations, okay? But it's the idea of making these assumptions that gets us to a model. So maybe a little bit small to see there, but you've got time step 1 pair, time step 2, you now have a mature pair, and then you keep going through and counting new pairs and mature pairs and so forth. And what you discover with this pattern is if you track the number of pairs in a month, so one pair in the first month, you add up the next month, this should start looking familiar. What do we have here, mathematicians? Indeedy do. It's a Fibonacci sequence, right? And so you can also figure out that there's a solution, 377 pairs, but the unexpected discovery was not only that this leads to a Fibonacci sequence, but that these Fibonacci numbers actually do tend to show up elsewhere in nature. So here are a few examples. There's our sequence. You may have heard about counting the rings in a sunflower. You go left and right, and you'll find 34 in one direction, 55 in the other, or 21 in one direction, 34 in another. So they tend to be in Fibonacci pairs. And you can see the same kind of spirals happening in pine cones and pineapples. And you can turn this into rectangles, where you can see what's happening here with this animation is you take a square, double it up, and then create another square with a side of twice the previous square. And then if you go ahead and draw a quarter circle in those, you end up getting Fibonacci spirals. And so if you have seen some of the recent memes with Fibonacci spirals put everywhere, don't laugh, because there is some validity to this, but the Fibonacci spirals put everywhere in the memes is kind of funny. Okay, so we see Fibonacci in art and music. And so I want to give you a chance to just listen to this one artist, David McDonald, who wanted to hear what it would sound like to play the Fibonacci sequence on the piano. So just relax and listen for a couple minutes.
The Fibonacci sequence is a series of numbers where each number is the sum of the previous two numbers. The numbers in the sequence have extraordinary mathematical properties and can be found in patterns all throughout nature. So I decided to see what they would sound like as music. To create the melody, I assigned the numbers 1 through 8 to the E major scale on the keyboard and added 0 and 9 on each side with the natural extension of the scale. I played the resulting melody with my right hand and added harmonies with my left hand. Now, the first number of the Fibonacci sequence is 0, but 0 added to itself just equals 0 forever. In fact, that's what you've been hearing in the background. In order to start the sequence, we need to add a 1.
And he starts all over again.
The Fibonacci sequence.
So it's kind of nice to be able to think about how we can cross over from some things we see in mathematics into art, but now we're going to get back to some science. So another breakthrough in mathematical modeling was created in pursuit of better understanding electrical signals in our bodies. So electrical signals are involved in so many of our systems, as you may know, including what we just used, our hearing, as well as vision, heart rhythms, and brain function. And clicking. Okay, and so I want to focus more on brain function and how math can yield some insights. Okay, so here's a picture of a variety of brains, from a rat to a squirrel to a monkey to a human. And as you know, we've been trying to unlock the mysteries of the brain for a very long time. So let's look specifically at the human brain. And we know some things. It weighs, on average about 1,500 grams and is made up of neurons, which are nerve cells, which makes up about half the mass of the brain. And they're depicted often like this, these nerve cells. So this is an image of how two neurons communicate, which is along this axon via an electrical signal, and that signal is called an action potential. But how did we learn about this mechanism of communication among neurons? So we have to narrow the question. Do we worry about the fact that the brain weighs 1,500 grams, right? Or do we worry about the non-neuronal matter? So you have to make some simplifying assumptions. How do signals propagate in tissue? So one simplified biological model, not math model, but a biological model, is the giant squid axon. And by that, we don't mean the giant squid, but we mean the giant axon of the normal sized squid. And in the normal sized squid, it's about 1 millimeter across, which for a squid is pretty giant. So Hodgkin and Huxley addressed this question of how electrical signals were propagated. And what they discovered was a major milestone in the science of the nervous system. So this here is the cover of the 1963 Nobel Prize program. Huxley is here on the left watching Hodgkin adjust an oscilloscope. They were awarded the Nobel Prize in physiology and or medicine. And their discoveries were considered iconic mechanisms. They discovered iconic mechanisms involved in excitation and inhibition in the peripheral and central portions of the nerve cell membrane. Okay, so they were interested in learning more about how cells communicate with electric signals, and they did two main things. First, they developed a method of gathering data, the voltage clamp, which I won't go into, but they actually produced this way of measuring an electric pulse. And then they created a system of differential equations to try to figure out the dynamics of that pulse. And you can see this is the system up here. This is the simulation. And you can see that it actually tracks both numerically and qualitatively the pulse itself. There are other beautiful pieces of work that have been done in math biology. Many of them have to do with looking at patterns. So, for example, how a leopard gets its spots, how stripes form on a tail. These are, you make use of reaction diffusion equations for these. You can model the Belousov-Zhabotinsky reaction also using differential equations with space. But I'm going to back up a bit and get back to a really simple way of thinking about things. How do biological cells grow? This is one of the very simplest models in biology that doctors learn when they're in med school. Okay, so you track cell divisions like bacteria over time, and you can use analogous dynamics for tumor cell divisions. So these can be bacterial cells or tumor cells, and you assume that you start with a cell and that it divides and that it becomes two cells and that it keeps dividing. So this continuous division process is actually the underlying dynamic that a lot of modelers use as a starting place for understanding cell growth. Now, there's an issue with this. It has been understood since, the late 1700s, and there's a mathematical way of describing cell growth. It's called exponential growth for the reason that the closed form solution is actually an exponential. And you can use it to calculate doubling time. But one of the challenges is one of the features of exponential growth is it doesn't look like it's doing anything for a very long time and then it shoots off. It really takes off. And so the question is, when is this actually reasonable? So what would happen if a quantity of cells that we had, say 1 milliliter of cells, doubled its size in a day, which can happen with some cell populations? That means in 7 days, you're at 10 milliliters, and in 14 days, you're at 100 milliliters. So if we wanted to use this for tracking tumor cell growth, for example, we'd have to figure out ways to change or modify that kind of model to make it more realistic. So now let's move on to the question of how to understand the spread of an epidemic. So one of the most used and now well-known since 2020-ish mathematical models for understanding epidemic spread is the SIR model. Okay, so there is a quiz, which you don't have to answer, think in your brain. What does SIR stand for? Sick, infected, and run down, simple implementation of reality, susceptible, infected, and removed, or please, sir, may I learn about how an epidemic model, have an epidemic spread? Okay, the answer is, what do we think the answer is? Susceptible, infected, removed. Okay, or infectious and recovered. So this model will help us determine a couple of terms that we had started hearing a lot about when COVID started spreading, and these were herd immunity and R naught. Do these sound familiar? We're not talking about them a ton anymore, but they will come up anytime there's another outbreak of anything, right? Herd immunity and R naught. So how do we determine herd immunity? So just show of hands, do we know what that is, herd immunity? Okay, so how would you describe it? Let's say, who would like to share their description of herd immunity? Yeah.
It's when people have become immune that the disease is not.
That's right. Enough people have become immune that even if there are still people who are not immune in the population, those people are also protected. There aren't enough susceptible people for the disease to continue. And of course, this question, what do bathtubs have to do with it? I will get to that momentarily. So in order to talk about herd immunity, we have to talk about what vaccines have to do with it. So the goal of vaccines is to protect an individual from getting sick, but there's a bonus goal, which we just talked about, to protect unvaccinated people from getting sick as well. And herd immunity, that term was actually first used for in the context of cattle. Okay, and that is actually the origin of the word, because Latin vaccinus, I don't know how it's pronounced, that's English cow, cow pox and smallpox were discovered to be related, and herd immunity is actually now discussed as herd threshold. But you probably know the story of how people who were working with cows that had cowpox were found strangely to not be as susceptible to smallpox. And so this sort of gave the idea of vaccination. Okay, so what is this R naught? It's called the basic reproductive number. And I'm going to illustrate this with these, a susceptible and an infectious individual. Okay, so this red ball is supposed to be somebody who's sick. The green ball is somebody who is susceptible to getting sick. And so let's say that you've got somebody who's sick and they have 4 friends that they cough on or sing at or something. And these friends are susceptible. Now, a basic reproduction number of 4 means that on average, during the course of a sickness, this person will make 4 people sick. Okay, so that's what happens. They may encounter other people, but on average, they will make 4 people sick. That's what the R naught stands for. So that's an R naught of 4. Okay, what unfortunately, if that R naught stays like that, then those 4 people each themselves make 4 more people sick, and then that's how you manage to get breakouts. So I want to share with you this PBS clip from It's Okay to Be Smart. This is what they did. They set up 500 mouse traps with ping pong balls. And what you'll see is yellow ping pong balls that are meant to represent a person who's susceptible to getting sick. And then they spring the mouse trap representing a ping pong ball getting sick and infecting others. And so let's see what happens. So 1 ping pong ball can spring a trap. Okay, so let's see.
Shot that in 4K at 1,000 frames a second. It was quite a slow start, wasn't
It
it?
was. I thought it wasn't going to work.
See that one sent into the middle.
Oh, that's amazing. This is exactly how a pandemic works.
It's like you got 2 outbreaks at the moment.
Oh, there they go.
Yeah, here it's going.
It's amazing.
You in the background.
I don't want to get a mousetrap to the eye. I'm not sure we're insured for that. This is currently where we are in the pandemic.
I think that one's me there,
Hiding in the corner. Keep hiding.
hiding at home.
This shows it perfectly, exactly how fast a pandemic can break out. It took a little longer in real life than 3 seconds, but it got bad. I'd say that worked. Except that this is a pandemic. I guess that's not a good thing.
Great demonstration though.
Yeah.
And this guy's happy as Larry. Look, he's still fine.
He's good. Way to stay home, bud. So how do you keep a pandemic from growing? Well, you have to give people immunity without them getting sick. And how do you do that? Vaccines. That's what vaccines are for.
Okay, so what is the goal? How do you want to keep the pandemic from growing? So what that means is you need this R1 to be less than, R0 rather, to be less than 1. So suppose an infected person coughs on 4 people, but at least 3 of those people are now immune. Okay, so now only 1 gets sick out of the 4. Okay, so in our model, we have susceptible, infected, and immune populations. Okay. The real beauty of now what happens with 3 of the 4 individuals being protected is that the illness really cannot spread that easily anymore. Okay, so this is the same setup, but now they've got white ping pong balls representing vaccinated individuals. And
now let's see this version in action, but with our mousetraps.
So now all of these white balls are sat on inactive mousetraps.
That's right. Those basically represent people who have gotten the vaccine. So they can't explode their coronavirus all over the rest of the table. And hopefully when we throw this in there, it'll look a little bit different than the last one. 3, 2, 1. You know, interestingly, we still had a couple of little hot spots, but the herd was immune.
Okay, playing back now.
Okay, we get a little bit of
A couple there.
just like it's like a bad family party.
See, that one landed on all the white balls.
And then we get maybe one more. It's perfect though. It's like those are like a buffer for all the other ones.
There's about 3 or 4.
But that makes sense because, you know, vaccines might not work 100% of the time, but they can protect the entire population, even though this is a lot less interesting than the first version.
Yeah, the more balls.
okay, so I think in that video, maybe 75% of the balls were white and the other 25% were yellow. But the question is, how do we figure out in real life how many of us need to become white balls and how many can afford to stay yellow balls? Okay, so how do we get this R0 to be less than 1? As we know, R0's a function of contagiousness, and it doesn't have to just do with COVID. We've been dealing with this for ages, measles and polio, for example. And there's some unfortunate stuff going on with polio recently, but the basic reproductive number of measles is very high, 12 to 18. So over the course of an infection, one person who's infected with measles can actually infect 12 to 18 other people. With polio, on average 7. So how do you figure this out? There's actually a very simple mathematical relationship, which is to take 1 minus 1 over that R0. So if you can figure out how to measure that basic reproductive number, then you can also figure out, okay, how much of the population needs to be made immune in order to stop there from being an outbreak. So it's not even complicated mathematics. So you can just think of this curve, and this curve is the minimum % of the population needing immunization so that we can eliminate the disease. In the case of COVID-19, I'm going to skip this because people actually know the answer, I think, in this room, but not every audience has known the answer. But anyway, you probably know COVID-19, CO stands for coronavirus, corona, whoops, and V, virus, disease, 19 for having been discovered in 2019. Okay, so what can we learn from this plot? So let's say that our R0 is somewhere around here, 2 or so. That means that we need to vaccinate maybe 60-ish% of the population in order to prevent any kind of outbreak. So any of that area up in the green, if we can get up into that area, will be good. Okay. Now, if the R0 increases, that means you actually have to make sure that you vaccinate a higher percentage of people. Makes sense. Okay, so your minimum vaccination level then goes up with R0 going up. Okay, now, here come the bathtubs. Here is what this has to do with this model. We actually think of the population of people as being kind of in their own bucket, but if they are susceptible, they can actually flow out into a bucket of individuals that are infectious, and those people can flow into a bucket of individuals that are removed. So you think of it as flowing from one bathtub to the next. This is how these models are often set up. So one thing I want to point out about the removed category is we often clump it together in one, but there is an important distinction between what kind of removed you are. If you're removed because you're dead, that's usually a lot worse than if you're removed because you're immune. And I think most of us would prefer to be in the immune category. So this is the category we want to maximize, the immune category. We don't want to maximize dead. How do we do that? One way to do that is to shrink the susceptible population. Some of you probably remember back when we really didn't know much about what was happening with this pandemic, that some people were saying, just let everybody get sick. You know, just let them get sick. It'll be like a big chickenpox party or something. Unfortunately, what that would mean is a much higher fraction of people ending up dead. So we don't want that. So we want to bypass that whole dead piece and jump right from being susceptible to being immune, if possible. Okay, now it turns out in some cases, vaccines can have been able to effectively eradicate some diseases like smallpox and rinderpest. But do we still need vaccines for measles? It turns out we do. That the level of measles incidence has been dropping significantly, but maybe about in 2016 or so, there was a big move to stop getting measles vaccinations. And I mean, it wasn't that big a move. It sort of dropped the level of vaccination from way up here to a little bit down here, but it was just enough into the red zone that we did see a spike from a low a couple of years before, about 130,000 cases worldwide, to up to over 800,000 cases in 2019. So it can make a really big difference. So we do have to stay vigilant. Okay, I'm gonna move over past these. And of course, you know, we travel like I just did, and we can keep spreading things around. Okay, now here's a question that there's a formula for that. Okay, the virus transmissibility rate times the number of susceptible people in the population divided by the rate at which people are being made immune. So if we want to make this number small, there's only a couple ways to do that with this simple formulation, right? What could we do? I want to make R0 small. Mathematicians, this is a fraction that the top, you make the top smaller, the whole thing gets smaller. You make the bottom bigger, the whole thing gets smaller, right? So what do we want to do here? Reduce N, yep. N, reduce B, or increase G, right? Any of those things. So the question we have to ask then is, what does that actually mean then in real life? Well, decrease B and or N, as you said, or increase G. How do we do it? And there are a variety of ways, right? So if we're looking at this little formula here, right, we can make the disease less transmissible, maybe by masks or social distancing. We can make fewer people susceptible, maybe by vaccination. We can decrease the amount of time a person is infectious, maybe by faster testing, quarantining, treatment procedures, all of those things. This is why we would hear all of these things, like do all those things, because no one thing is going to be the answer, right? It all goes into this formulation. So that's why we heard all of these recommendations. I also remember early on just being told, wash your hands a lot. You know, I mean, I think it's always good to wash your hands a lot. I'm not sure how useful that is in this case, but here's a question. What do you want to know about your own SARS-CoV-2 antibodies? And you can't answer this question on the poll because apparently it's not working with this setup. But if you just think to yourself, do you want to know today if you have antibodies? By the way, antibodies are part of your immune system that the more of them you have, the more likely you are to be protected. Okay, so do I have a high active immune system? So do I have antibodies against getting coronavirus? If I do I have enough of them? Or Do you want to know what happens in the future? If I know my antibody levels now, can I figure out what they are in the future? And should I get a booster vaccine? Oh, look, somebody answered that poll. Okay, so it turns out that data can tell us the answers to things about today, right? Today, I can look at data and say, do I have antibodies? I can take a blood test. And do I have enough to protect me today? But math modeling tells us about tomorrow, right? So if I know my antibody levels, can I predict if in the future there'll be enough to keep me from getting sick? And how frequently should I get a booster vaccine? So there actually were a flood of new mathematical models created to explore this epidemic spread. But I was actually asked by a local biotech startup to help them understand mathematically if we could learn anything using the assay data that they had developed, where they could take blood tests from people and determine the amount of active antibodies in their system. So it wasn't just counting, but it was actually measuring how effective your own blood was at stopping a virus from entering your cells. So it was kind of an interesting assay that they did. So they wanted a really simple model. And so we had to make assumptions, just like we talked about. So I'm going to assume that the antibodies have to be triggered. Once triggered, each of us has a different ability to maintain different levels. And the goal was to figure out in an individual specific way if we could make predictions about our protection in the future. So, so there's actually this paper that you can read by me and other people, where we answer this question: why, when you have two different individuals both getting, say, 2 doses of a vaccine, one of them gets sick and one of them does not? So there's the process of getting the assay data, creating the model, finding the individual parameters, and then we can actually see the differences in the outcomes between 2 different individuals, both vaccinated in the same way, but both with different personal biological parameters that make the outcomes different for each one of them. We also noticed something else kind of interesting in this data set, and it's, in my mind, is a relatively small data set, so I didn't want to extrapolate too much from that. But one of the folks I was working with said he could tell if you gave him the data from a husband-wife pair, he could always tell you which one was the wife and which one was the husband without looking at any other identifying information. And why is that? Well, he said that overall, he noticed stronger immune responses in the women than in the men. So this is one way of looking at it. The green and the blue here are from strong to very strong responses at last sample taken. And so this side is women and this side is men. So that's at one time point, but what you can do with the model is look at multiple time points. So this is an example of husband-wife pairs. And you can see overall that the women on the left tend to have overall stronger responses than the men on the right, which is interesting. We didn't think we could necessarily extrapolate anything from that, but there has been a retrospective study that actually showed that women overall tended to have increased resistance to viral, bacterial, fungal, and parasitic organisms, and higher innate immune responses. They think it has to do with estrogen, I don't know, it's their hypothesis, and that men were more at risk of severe infection and mortality. So that seemed to be consistent with the data that we saw. But let's connect some of these concepts now. So oscillating behavior is something that shows up also a lot in nature. At a population level, predator-prey interactions show oscillating behavior, and immune cancer interactions show oscillating behavior. So how do we connect these? How is a lynx like an immune cell? So this is another example of how very different natural systems share similar significant features. Okay. So you can see plots of data. This is actual data taken over many, many years by a Canadian fur trapping company. And you can see this sort of cycling behavior that happens. This is lynx capturing hare. So they track the lynx population and the hare population. And this periodic behavior led to these famous predator-prey equations. So periodic behavior, you can see it in chemical reaction. Lotka looked at that, and Volterra, about 6 years later, noticed oscillating levels of fish in the Adriatic. And together they came up with, well, actually independently, but I guess they talked about it after, they came up with this famous predator-prey model. So I'm not going to go through the details, but again, for the mathematicians, a very simple two population model. Okay, barely nonlinear. So you can take that model and you can see simulation results. And so taking a small bit of the actual data, you could actually create a model that tracks those data pretty well. Okay, I'm going to show you something here that's not math now, but it's from outside my house back home. Okay, I was sitting last July, I was sitting at my desk at like 6 in the morning on a conference call back east, and I saw something go past my window. And I wondered what it was. And so my husband went and looked at our security cameras and said, look at what this was. So watch what went past my window. See if I can. Can you tell what that is? It's a bobcat. Yeah, we do have mountain lions too. They're much bigger. Yeah, so these are smaller, and it was chasing a rabbit, and the rabbit escaped, in case anybody's worried. So no rabbits were harmed in the filming of this video. You can see there it is, sort of coming across the back. So anyway, I saw that and I was like, oh, predator prey in real life. Okay, so this question that I just skipped over because the poll is not working has to do with how many people in the audience, you don't have to raise your hand, but just think, do you know someone or who has had or is having to deal with cancer? In general, yep, I do. I think it's the majority of us do. Okay, so it turns out that over a lifetime, the risk for a woman to develop some form of cancer is 1 in 3, and the risk for a man is 1 in 2. So this is something that still needs to be dealt with. Now, I'm not going to ask you to answer these questions, but what is true about the immune system? Is it the case that the immune system is not really connected with cancer? If it were, it wouldn't be there in the first place. I'm going to tell you that's wrong. But where did this statement come from? It came from one of the early medical conferences that I went to, where I was presenting a math model of cancer and immunology, and somebody stood up well, you know, I have a question, which is really a comment, right? Here's the comment: the immune system has nothing to do with cancer. Why are you wasting your time with this? So that was delightful as a young researcher to hear that, right? Turns out that guy was wrong. We were right. And you've probably now seen ads all over television and everywhere else about ask your doctor about Keytruda and all other kinds of immune modulating treatments for different kinds of cancer, right? So it does have something to do with the immune system. It's basically just logical, right? If we said the immune system has nothing to do with that, or you'd never get sick, then none of us have immune systems, right? Because we get flus, we get colds, we get all kinds of things, and our immune systems respond. And it's the same way with cancer. Sometimes the immune system is effective and can control the cancer, and sometimes it's not. And that's what we want to understand. So is it the case that if we're generally healthy, our immune system ensures that we're less likely to get cancer? There's a correlation, but you know, it's hard to say. Our immune system can be harnessed for use in cancer treatments. That is true. And do they have minimal to no side effects? That's not quite true. There is an issue with autoimmunity being triggered. And so even though immune treatments on the whole tend to be less toxic than some of the older chemotherapies, you still have to be careful with messing with overstimulating your immune system. Okay. All right. So predator-prey model, this is what we do. You notice here's another set of oscillatory behaviors, but this is now a tumor. This is actually measured in a particular patient who had breast cancer and was being treated. And the treatments were happening, it's a little bit hard to see, but they're happening at regular places, yet her cancer would sometimes grow after getting treatment and sometimes shrink after getting treatment. It seemed to just oscillate like this. And so the question is, what is happening and why is that taking place? And so we thought, well, maybe the response of the immune system has something to do with that, because the predator-prey interaction of the lynx and the hare, or the sharks and the fish, leads to this natural kind of oscillation. And so we thought about implementing that as a within host model. So this is kind of an interesting, I want you to see this video. This is an actual video of T cells, which are part of your immune response, killing cancer cells. It amazes me that people can get these videos. It's crazy. So if you look at that cell where the arrow is, there are 3 T cells. This gives you a sense of size, ganging up on that cancer cell and actually killing it. And the thing just sort of blebs and dies. So it's really interesting. And we use these kinds of ratios to try to work out what the parameters should look like in our models as well. All right, let me go forward here. Okay, so immune cells, normal cells, and cancer cells are what we put into our first model that we worked on. So it kind of looks like a predator-prey model, but there's a third element in there. And we put the normal cells in just so we could keep track of health. Because one of the issues with chemotherapy is it makes people violently ill in many cases. You can give lots of chemotherapy to a mouse and they don't complain, right? So they can get very high doses, but when you move from mouse models into human models, it gets really tricky. And so we tried to keep a level of health in there as well. And we also get these oscillatory behaviors. So since we're coming near to the end, I'm not going to go into how we were able to capture some of these data from real experiments, but there is this relatively new clinical confirmation about the predator-prey dynamic, and this just came out in 2019. So our first predator-prey cancer model was published in Cancer back in 2005. So this is, you know, almost 15 years later, where these folks discovered that they could see a predator-prey-like relationship between circulating immune cells in abundance and tumor size in patients that responded well to immunotherapy. So it was really fascinating to see that what we had hypothesized 15 years earlier was shown to be actually relevant back in 2019. So I just want to end with saying that math models can help us see common dynamic structures across nature. And I would say model is good if it can answer the question we ask. And I'd say it is awesome if it can help us discover new truths. Okay, thank you.